Welcome to this explainer. Today, we're diving straight into something absolutely mind-blowing. We're going to completely demystify an instrument that allows scientists to measure the impossibly small. It's called Michelson's Interferometer. We're going to look at everything from its internal anatomy right down to its real-world applications, breaking down exactly how this brilliant piece of engineering actually functions.
So think about this for a second. How exactly do we measure distances that are literally smaller than a single wavelength of light? It's a real brain teaser, right? Because it forces us to find a mechanical solution to a completely invisible problem. Obviously, our standard rulers or even highly precise micrometers just aren't going to cut it when we're dealing with the incredibly microscopic scale of light waves.
Well, to solve that exact problem, scientists rely on the interferometer. Now, what is that? By definition, it's an instrument based entirely on the phenomenon of interference, and it's used to make incredibly precise measurements of wavelengths and insanely tiny distances. Basically, it cleverly overlaps light beams to reveal measurements our eyes could never, ever see on their own. It's like a giant puzzle made of light.
So here is our roadmap for the explainer today. First, we'll look at splitting the light beam. Second, we'll step inside the interferometer itself. Third, we'll decode the interference fringes. And finally, we'll talk about measuring the invisible.
All right, let's jump right into Section 1, splitting the light beam.
The absolute core principle that makes all of this possible is known as the division of amplitude. Here's what that means in plain English. A single beam of light from an extended source is divided into two parts of equal intensity. And this happens through partial reflection and refraction. Basically, we're taking one solid beam of light and cutting its intensity perfectly in half. This is crucial because those two new beams can then travel in perpendicular directions and eventually overlap later on.
Now that we've got the core principle down, let's move on to Section 2, inside the interferometer. Let's see how this thing is actually built. Okay, taking a look at the construction blueprint here, there are a few key players. First, we have a partially silvered beam splitter, which we'll call G1. Right next to it is a compensating plate, G2, which shares the exact same thickness as G1. Then we've got our plane mirrors. Mirror M1 is mounted on a little carriage controlled by a super precise micrometer screw so it can move. Mirror M2, on the other hand, is stationary but adjustable. Now, the really important detail here is that plates G1 and G2 are held perfectly parallel to each other, and they're inclined at a strict 45-degree angle to mirror M2.
Let's trace the actual journey of a single beam of light through this maze. Step 1. Our monochromatic light passes through a collimating lens, which makes the rays perfectly parallel, and it smacks right into that beam splitter, G1. Step 2. It splits. Part of the light reflects off the back of G1 and travels along path AC up to mirror M1. The rest of it transmits straight through along path AB towards mirror M2. Moving on to Step 3, both of these newly split beams hit their respective mirrors and bounce straight back to G1. And Step 4, well, this is where the magic happens. The beams overlap, reflecting and transmitting down a brand new path, AT, right into our viewing telescope. Since they originally came from a single source and their amplitude was perfectly divided, they're what we call coherent. That means when they crash back together, they create interference. But wait, if you compare these two paths, you'll notice it's a completely uneven journey. Path AC actually passes through the glass of beam splitter G1 twice during its round trip. But path AB, it only passes through that glass once. So to compensate for this uneven optical path difference, we insert that compensating plate, G2, directly into path AB. This perfectly levels the playing field, ensuring both beams travel through the exact same amount of glass.
With our light beams perfectly compensated, let's move to Section 3, decoding the interference fringes.
When we finally look into the telescope, we don't just see light. We see mirror M1 overlapping with a virtual image of mirror M2, and how these two line up totally dictates the output we see. If the mirrors are perfectly perpendicular, we get circular fringes. These are concentric circles formed by a completely uniform air film, and they're known as Haidinger fringes. But if you incline the mirrors even a little bit, creating a wedge-shaped air film, we get localized fringes, which look like straight or slightly curved lines. And if you decide to switch things up and use a white polychromatic light instead of a single color source, you'll actually see beautiful colored bands with a central dark fringe.
Now, this next part is absolutely fascinating. There is a striking visual confirmation of complete destructive interference. If mirror M1 and the virtual image of M2 exactly coincide, meaning they perfectly overlap with zero path difference and no air film between them at all, the entire field of view goes perfectly dark. No light whatsoever. It's crazy to think about, right?
Okay, let's head into our final section, Section 4, Measuring the Invisible.
The interferometer isn't just a neat optical toy. It has some heavy-hitting, real-world practical applications. Scientists use it for determining the exact wavelength of a monochromatic source. It's used for finding the minuscule difference between two neighboring wavelengths to resolve spectral lines. It can calculate the refractive index and thickness of super-thin transparent materials. It's even been used to measure the standard meter in terms of the wavelength of light. These applications really prove that this machine is a foundational tool for absolute precision in physics.
So how do we actually do the math here? It's surprisingly elegant. The equation is lambda equals 2 times d divided by n. In practice, what you do is set the mirrors to get those circular fringes we talked about. Then you carefully move mirror m1 a known distance. That's our d. As you move it, you literally just count the number of fringes that cross the center of your field of view. That's your n. Plug those two numbers in and boom, you extract the exact wavelength.
Let's put that into perspective with some real numbers. If you move the mirror a ridiculously tiny distance, just 0.0589 millimeters, and count exactly 200 fringes crossing your view, you do the math. Multiply that distance by 2, divided by 200, and it yields an incredibly precise wavelength, 5,900 angstroms. Just like that, using a mechanical screw and some mirrors, we've accurately measured the invisible.
But it gets better. We can also measure physical objects. Let's say we insert a really thin, transparent sheet into one of the light paths. Because light travels slower through that material than it does through air, it creates an extra path difference. That difference depends on two things, the thickness of the sheet, T, and its refractive index, mu. So if we know mu and we count the number of displaced fringes, which we call m, we can calculate the exact thickness of that sheet. The formula is T equals m times lambda divided by 2 times mu minus 1.
Let's look at one more example to really hammer home this incredible sensitivity. If we use a yellow light with a wavelength of 6,000 angstroms and we count exactly 100 displaced fringes, we can calculate the exact microscopic distance the mirror moved. Working that formula backward yields a displacement of exactly 3 times 10 to the negative 5th meters. That is absolutely astonishing, absolute precision.
As we wrap up this explainer, I want to leave you with this one final thought. If we can measure something as fundamental as the standard meter using just the delicate microscopic overlap of a single light wave, what other invisible barriers of our physical universe are we now equipped to break? Mastering the manipulation of light truly opens the door to understanding everything else around us. Keep that in mind the next time you look at a simple beam of light. Thanks for exploring this with us.